So everybody who likes drain tanks, this is a drain tank.
The big goal of this machine here is to simulate how decay heat is removed from this design when there's a shutdown.
That is correct.
In January 2015, Kirk Sorensen of Flibe Energy toured UC Berkeley's compact integral effects test for pebble and molten salt fueled reactors. Kirk also presented at UC Berkeley.
We're going to talk mostly about the chemical processing and a little bit about the power conversion system as well.
And the University of Utah.
The chemical processing of this reactor.
Those two presentations are combined in this video.
We're in a situation in our country where we're retiring a lot of power generation right now, and this is actually happening particularly in the eastern U.S. where I live. You can almost trace the outline of rivers like the Tennessee and the Ohio based on where these retirements are taking place. Now, there's things we don't like about coal, and there's things we do like about coal. We like the fact that it is a reliable energy source. We don't like the fact that it emits a lot of pollution, and it's not a resource that's going to last forever. There's also new regulations that are coming out that are accelerating this change. So we've got a big job to do, and we don't really have a great deal of time to do it. We need a source that mimics all of the benefits of coal-fired power and tries to eliminate the drawbacks. And a number of us are convinced that this energy source is going to be nuclear in origin. And the reason for that is the energies of the nucleus are about 2 million times greater than the energies of the electron cloud, the energies of chemical energy, the energy that powers combustion, digestion, all the processes we're used to. Yet out there in the universe is powered by the energies of the nucleus, changing nuclear states, fusion and fission and nuclear decay. And humanity has only realized this in about the last 70 or 80 years, to where we've taken our first steps into a nuclear-powered world. And I'm convinced that if we are going to be able to enjoy the industrial society that we have, enjoy reliable energy, and improve its cleanliness, we're going to have to make this leap too. We're going to have to make the leap to nuclear energy. I kind of feel bad when I hear that nuclear reactors are being retired, even though I know that they're not as efficient as they could be. They're still a whole lot better for the environment than spewing dirty coal into the air. What I'd really like to see is the United States building new nuclear resources to replace our reactors that are being retired, the uranium-style reactors, and also to be able to replace coal and fossil fuels. The Department of Energy has put the responsibility for these new nuclear reactors, though, squarely in the lap of industry. And this is a big deal because for decades in this country after the war, the Atomic Energy Commission made all the decisions about what was going to happen. It wasn't like industry got to say, oh, we want to try this or we want to try that. They said, we're going to do this or you're going to do that, and submit a proposal. But it was not in industry's court to go and make decisions like this. And now it is. And this is a relatively new development. And I think it's going to lead to entrepreneurialism because they've squarely put the onus on us to say, how's nuclear going to go forward? Make your business case, make your argument. If you want a nuclear power plant, say why it's better. Now, what kind of nuclear energy then becomes a logical question? We are blessed on this world with nuclear resources. 3 forms of nuclear fuel, 2 forms of uranium, and 1 of thorium. Now, thorium is about 3 times more common than uranium. But the uranium we're using today is only a tiny, tiny, tiny fraction of natural uranium. It's what's called naturally fissile uranium, uranium-235. This is what we're consuming right now for nuclear energy. If you want to make nuclear energy a sustainable enterprise, then you need to go and be using the remainder of these fuels. And thorium has the advantage of abundance. There's an awful lot of it, but it doesn't have any naturally fissile thorium. There's no little sliver here that we can point to and say, this is thorium we can use to start a nuclear reaction. This is one of the reasons why thorium has not been favored for nuclear energy in the early days. But now we've reached a more mature stage where I think it is time to go ahead and look at implementing thorium as a nuclear fuel. Now, both thorium and uranium-238 can become nuclear fuels by absorbing a neutron. And this happens inside a nuclear reactor. And this is what Glenn Seaborg figured out right here at Berkeley, 70 years ago, was that this was possible. Glenn Seaborg, wow, what a guy. Read all you can about him. If thorium absorbs a neutron, it becomes uranium-233. That is now a nuclear fuel. It can fission, it can split and release energy. Uranium-233, when it's fissioned by a thermal neutron, will produce about 2.3 neutrons net. And that's important because we needed 2 right here to make this happen in the first place. So you got to have more than 2 to keep this going. The same thing can happen with uranium-238, which is the common form of uranium, the abundant form of uranium. If it absorbs a neutron, it becomes plutonium-239, and then that can fission and also release energy. So in both ways, you can turn these abundant nuclear resources into energy sources. So what's the advantage of thorium then? Why think about thorium? uranium-238 is converted to plutonium through a neutron, but that's thermally fissioned. On net, you only get about 1.9, so you're below 2, you're below that threshold, and that's why we can't build plutonium breeder reactors in thermal spectrum reactors. Just can't do it. There's not enough neutrons. And really, plutonium kicks out enough neutrons. It's just plutonium has a real propensity to eat neutrons too. So if we want to use plutonium efficiently, we've really got to go to a fast spectrum, because what happens in fast spectrum is fast neutrons have a much higher probability of fissioning the plutonium without being absorbed. Now, because they have a higher probability of doing that, though, they don't have a higher probability of the fission happening in the first place. This is what plutonium looks like to a slowed down neutron, and the blue is the probability that it will fission, and the red is the probability that it will simply absorb the neutron. And this is what plutonium, each one of these guys is what plutonium looks like to a fast neutron. Every one of those is a better quality hit. You know, you're not going to get an absorption, but you need a lot of it. So if you want to have the same amount of cross-section probability in fast as thermal, you've got to have a lot of fuel, And so this is a advantage thermal spectrum, because you need a lot less fuel. But because you can't breed in thermal spectrum, the interest has always been for plutonium breeding to go to the fast spectrum. And I bring this up because thorium doesn't have this issue. Thorium can go ahead and be used as a nuclear fuel in a reactor with slowed down neutrons, what's called thermalized neutrons. Now there's a few steps thorium goes through on this way. It first absorbs a neutron and becomes thorium-233, going from 232 to 233. See, the math's not so hard, just +1. And then that thorium-233 will decay over a period of about a half an hour into another element, protactinium-233. And protactinium is a naturally occurring material. It's part of the decay chain of uranium-235. But that's protactinium-231. It's got something like, I think, 172,000 year half-life. But this stuff, protactinium-233, has a much shorter half-life, about 30 days. But still, in terms of reactors, that's pretty long. And it drives a lot of what I'm going to talk about today with the chemical processing. But ultimately, it will decay to uranium-233, as long as it doesn't absorb a neutron, and it has a very quality fission. About 91% of the time, it's going to fission rather than absorb. And that makes U-233 the best fuel in the thermal spectrum. It outperforms everything else. And it's one of the reasons we really get a kick out of thorium. So there's three options. We can keep burning U-235, and without getting into issues about like seawater uranium, it's just we're using a very small amount, and we're not using a whole bunch of uranium. We can go with the fast breeders I saw yesterday at INL with EBR2. Or we can potentially take this tack of a thermal breeder with thorium. I think the path that we want to go is the thorium, because of its abundance and because of the fact that we can use it with slowed down neutrons. That makes the reactor design simpler and quite possibly safer. Now, if you can operate a thorium reactor without any uranium-238 present in the fuel, then you can really reduce the amount of transuranic waste you're going to generate. And the reason for that is the thorium absorbing a neutron, each one of these vertical steps is a neutron absorption. So thorium absorbing the neutron, 90% of the time will be fissioned by the next neutron. Now, 10% of the time it will go to U-234, which will absorb another neutron, going to U-235. Think of these as like off-ramps off the freeway. So if 90% of the cars exit the freeway on the first off-ramp, and 85% of the cars that are left over exit the freeway on the next off-ramp, how many are there to make your first transuranic? Only 1.5%. So with the thorium cycle, you could potentially get down to 1.5% of the long-lived waste production of the uranium cycle, and that's a big advantage. On the other hand, when you got a fuel like in a uranium reactor, it's got a lot of U-238 in it, then it's only one neutron away from its first transuranic. And the reason I bring up transuranics is they govern in large part our waste disposition strategy. In fact, actinides in general govern our waste disposition strategy because they have long half-lives, they have complicated decay chains. Our waste disposition strategy is in great part about actinides, and we've got one of the members of the Blue Ribbon Commission here, so stop me at any time if I screw up here. So here's what we're doing now. This is the red line on a log chart. Any line on a log chart, tread lightly. But this is how long it takes our spent fuel to reach the same radioactivity as natural uranium. It's about 300,000 years. If you can keep all the actinides out of the waste stream, then you can really shorten that to about 300 years. So one of the goals in the chemical processing system I'm going to talk about today is how to keep the actinides out of the waste stream. I hate to even call this stuff that is made by the thorium cycle waste. Neptunium-237 is actually used to produce the material that NASA uses for batteries in their deep space probes. Have you ever heard of the Curiosity rover on Mars? Anybody heard of that or followed it? That's being powered by plutonium-238, which comes from this neptunium. Anybody following the New Horizons mission to Pluto? Keeping track of that? Yeah, that's also powered by this stuff. So even our waste, so to speak, isn't even really waste. It's something that we can go and make very useful products out of. Like I said, I was at NASA, so I'm really into this kind of stuff. By the way, 2015 is going to be a really exciting year for NASA because we're going to see Pluto for the first time, and we're going to see the largest asteroid in the solar system, Ceres, for the first time. So cool stuff coming up this year. if you use thorium with this kind of efficiency, something really amazing becomes possible. And this was realized almost immediately by Glenn Seaborg. He thought, you know, every cubic meter of the Earth has got a certain amount of uranium and thorium in it. It's about 2 cubic centimeters of thorium and half a cubic centimeter of uranium. If you can use thorium to the kind of efficiencies that we're talking about today, the energy equivalent of these 2 cubic centimeters, so imagine 2 little sugar cubes, you know? Think of 2 little sugar cubes of thorium metal. Now, Milan, can you hold that in your hand? 2 cc's of thorium, is that going to hurt you? No, that's not going to hurt you. So you can even imagine doing this. This has the energy equivalent of more than 30 cubic meters of the finest crude oil or anthracite coal. So this is like taking any worthless piece of dirt anywhere in the world and turning it into a multiple of the finest chemical energy resources we have. I mean, that's absolutely amazing. That's something that just completely changes our paradigm about relative national wealth and resources and so forth. That means worthless pieces of dirt become potential energy mines. Now, good news is we don't have to mine average continental crust for thorium. There's lots of places where nature has already pre-concentrated thorium in much greater concentrations than this. The nuclear concept that we would like to put forward involves what's commonly called a small modular reactor. There are a number of different kinds of small modular reactors. A lot of them are proposed to use the same kind of water-cooled reactors and uranium that we use today, but our reactor design would be using a molten salt. And a molten salt is just that. It's some kind of salt mixture that has been taken to a higher temperature and then melted. But one of the things I think is real remarkable about these salts is they form very stable compounds, very chemically stable compounds. And this allows them to serve as an ideal medium inside a nuclear reactor. The process by which we would try to use thorium in the reactor involves introducing thorium into an outer region of the reactor called the blanket. And in the blanket, the thorium would absorb the neutron. It would take that first step, remember 232 to 233. It's going to absorb a neutron, and it's going to begin the process of becoming uranium-233. Now, as it takes those steps of decay, turning into other elements, protactinium and then uranium, we can employ a chemical separation to remove those new materials from the blanket and then introduce them into the salt that is going to go in the reactor core. And that's the place where the fission reaction is going to take place. That's the place where it's going to generate additional energy. This technology has been demonstrated to a degree before. This is a reactor experiment that was built at Oak Ridge National Labs in the 1960s. It was called the Molten Salt Reactor Experiment. And it was an attempt to demonstrate some of the important technologies that would be used in the thorium reactor. You nuclear engineers are probably going to think those are fuel rods. They're not. They're graphite. The fuel was a liquid that flowed through channels in this graphite. The graphite served as the function that water serves in an existing solid-fueled reactor, which is to moderate the neutrons that are being born in fission. Except this time, instead of having solid fuel and a liquid moderator, you've got liquid fuel and a solid moderator. This reactor didn't use thorium, but it did use uranium-233 that came from thorium. And it was considered a first step. It was considered that inside part of the thorium reactor concept. It used a heat exchanger to move the energy from the salt that ran through the reactor to another salt that rejected that energy to the environment. This is the radiator that it used, glowing cherry red. And it didn't generate electricity with that energy, but it did demonstrate that the reactor was capable of operating in a stable manner and being very responsive to the people that were controlling it. Here's a picture of what the reactor cell looks like, and there's a fellow, so you can get a sense of how big it was. This was not a terribly optimized design. This was something that they had put together very quickly because they had some funding available, and it was meant to demonstrate materials and technologies. Ran for about 5 years, and it was very successful. I talked to some of the people that actually operated the molten salt reactor experiment. I said, well, what was it like to run this experiment? They said it was boring. It was boring. And I thought, well, you know what? That's exactly what you want to hear a nuclear engineer say. You know, you don't want it to be exciting. Yeah. Another aspect that was emphasized to me by one of the people that had worked on this reactor, his name was Paul Halbenrich. And he said, you know, lots of people told us that we could build molten salt reactors. But they also said they will never be practical. You will not be able to maintain them because of the mobile radioactivity, because of the fact it's moving around a loop. He says, I am more proud of the fact that we maintained that reactor for 20,000 hours successfully. We had a high uptime than any other aspect of the molten salt reactor experiment. And I really think that's worth mentioning. You know, this was a first of a kind experiment, and yet they were able to execute so much of their research plan and have such a high uptime because of the admirable characteristics of this. And I think Paul is actually that guy in the picture right there.
Here we have the potentiality of a whole new breakthrough in the development of power for peace. And that means jobs for this area, but jobs and power for hundreds, for millions of people all over the world. At the time of that announcement, I was able to announce we were going to have one experimental plant to go forward.
Unfortunately, in 1969, Richard Nixon decided to cut the funding for advanced research at the Atomic Energy Commission. And so the Atomic Energy Commission, which was overseeing all of this work, had to make a choice. They had to decide which of these advanced reactors they would continue with. Would it be the thorium one, or would it be reactors that were based on plutonium? And they made the decision, unfortunately, to pursue the plutonium reactor rather than the thorium reactor. And this is one of those times in history, I think, we made a big mistake. You know, we had an opportunity to go forward with this thorium technology, and we chose not to do it. And their goal was to build a large plutonium reactor on the shores of the Clinch River in Tennessee. Now, this ended up getting canceled and in the late 70s when Carter took office. And it's one of those things where I wish that maybe when they had decided not to do the plutonium route, they had gone back and said, well, maybe we should have kept going with thorium, because thorium showed a lot of promise. Carter was really concerned about nuclear proliferation. He was concerned other countries were going to try to take nuclear technology and we're going to use it to make nuclear weapons. And the irony is thorium technology had been rejected back during the Manhattan Project precisely because it was not applicable to the nuclear weapons program. It's one of the reasons why the technologies for uranium and plutonium were moving forward in the 40s and the 50s and the 60s at a much faster rate than the thorium technology was. It's because they were applicable to the weapons program and the thorium technology was not. Well, not a great deal was happening in the Western world in terms of thorium development for many decades, although the Indians have been pursuing thorium consistently for many decades now. Most of that time they've been looking at thorium oxide fuels, solid fuels, and running the same challenges with solid fuel thorium that everybody does. But I was told at this recent conference in fall of 2013 that they are now beginning, they have a group that's starting to look at the molten salt idea. And I have been told informally through friends of this person that one of the former directors of the Indian nuclear program, when asked, if you had it all to do again, what would you do differently? He said, I would have gone to molten salt right from the beginning. I found out about this technology in about 2000 when I first started at NASA, and I got very excited. I was thinking about space reactors and so forth, but it didn't take long until I was thinking more about how do we power our world right here on Earth. You know, if we can do it in space, why don't we do it here on the Earth? I was listening to a fellow out in the hall, and somebody asked him, well, why are you here? And he said, well, because I'm interested in clean air and clean energy and things like that. And I felt exactly the same way. That's why I was increasingly interested in something that wasn't in space but was right here on the ground. Let me get a little more to the specifics now of what I'm working on now in cooperation with the university here. And this has to do with the chemical processing of this reactor and how you go and remove particular materials and introduce them in other places in the reactor. This is where I began from, which is a schematic I got from a 1967 document from Oak Ridge. And this was the only thing of its kind. The basic idea is you've got to move fuel that you've now made in the periphery of a reactor. You've got to remove it chemically, and you've got to go introduce it into a different fluid stream in the reactor. And you have to take advantage at each step of chemical differences that are there and things that you know about those materials. So I've had to become very, very familiar with slight differences between thorium, protactinium, and uranium in order to understand these particular separation and production sequences. So here's the big picture of the liquid fluoride thorium reactor that Flibe is working on. Essentially, here's the reactor. It's got a lot of graphite in the core. The green fluid is the fuel salt. This is a combination of lithium, beryllium, and uranium fluorides. So this is the material that's undergoing nuclear fission. The uranium in this is undergoing nuclear fission and generating energy. So as that fuel salt is pumped out of the core, it heats another salt, a coolant salt, which is just a lithium beryllium fluoride salt. And then that salt is then used to heat carbon dioxide gas, which passes through a gas turbine and generates electricity at high efficiency. This design will generate electricity at about 45% efficiency. Now, you mechanical engineers out there will go, 45%? That's awesome. That is incredible. For all you out there that aren't mechanical engineers that go 45%, are you kidding? That's like an F minus. You know, you have to believe me. Mechanical engineers get super excited about converting thermal energy to electrical energy, anything better than about 30%. That's just considered super duper great. So 45%, incredible. And then on the other side of the reactor, we have the chemical processing system. In the first step, this blanket salt, which has the thorium in it, is passed through what's called a reduction column. And in that reduction column, a metallic stream of bismuth contacts the blanket salt in a countercurrent fashion. They're going one against the other. And protactinium and uranium that are in that blanket salt are going to dissolve into the bismuth. And that allows them then to be removed from the blanket salt, and the blanket salt returns back to the reactor to continue generating new fuel. Now that the protactinium and uranium have been removed, they pass through another reduction column into an electrolytic cell. And in this electrolytic cell, they are oxidized from being metals into being fluorides. At the same time, part of the decay salt is being electrolytically split apart into a metal stream, and that metal stream is then entering into the bismuth in order to return back to serve as a reductant. The upshot of the whole thing is you're going to move these new nuclear fuels out of the blanket into a decay salt. And the reason for this is that 1 month period. It takes a month for protactinium-233 to decay to uranium-233. You want this to happen outside of the reactor. And the reason you want that to do it is because it has a propensity to absorb a neutron inside the reactor if you leave it there. You do not want your protactinium to absorb a neutron, become protactinium-234, which then decays to U-234, which is not a fuel. So I'll just tell you right there. Neutrons, bad. We don't want neutrons to happen after we've already turned into protactinium. So protactinium goes into the decay salt, decayed uranium comes out. And the decay salt is just meant to essentially continue. Yeah, but it's a different salt. It's fairly close in composition to the blanket salt, but it's not exactly the blanket salt. Here's the blanket salt coming in. You can see it's got lots of lithium, lots of thorium, 15 ppm protactinium. And then here's the decay salt, 68% lithium, 29% thorium, but 8,900 ppm protactinium. So it's got a lot of protactinium. The decay salt is where protactinium is supposed to go and never come out. So that's where it lives. What we want to take out is uranium. So that decay salt then passes to a decay tank, and this is also where we add thorium tetrafluoride as a makeup material over time. It's a very, very small addition, but this is where thorium actually enters the chemical processing system. So we leave the protactinium outside of the reactor, allowing it to decay to uranium. Once it's decayed to uranium, we're now in position to implement another cool chemical trick, because uranium will absorb additional fluoride ions in what's called the fluorination column. And it will go from being a liquid, uranium tetrafluoride, into being a gas, uranium hexafluoride. And that's a separation step that we can employ. The good news is the other things in the material don't do that. Protactinium doesn't change, thorium doesn't change, lithium beryllium doesn't change. So it's a way to extract the uranium that we now need to fuel the fuel salt. So here's the fuel salt coming out. I'm going to hold up in the drain tank for a little while and just kind of cool down because it's got lots of fission products in it. And then it's going to be introduced into the fluorinator. And the fluorinator is also going to, this is the fuel fluorinator, this is going to remove any uranium present as UF6. And it's very, very important to get high fluorination effectiveness on this one. This one, it doesn't matter so much. If we miss uranium on this guy, we're going to get it up there in the redex, and it's going to stay in the salt. It's not a big deal to lose it. This guy, we really, really need to get as much of that uranium out as we possibly can. Because after the uranium comes out as UF6, the result is going to go to another reductive extraction column, this time using lithium as the reductant alone, no thorium or anything. And this reductive extraction column is essentially going to pull all the fission products out. So by dialing that lithium up enough, lithium will essentially replace everything in the salt, other than things like noble gases, which have already come out anyway. So that's why it'll also pull out uranium. So we want to make sure we got the uranium here, not here. So then the salt, having been stripped of fission products and uranium, then proceeds to a reduction column where it is contacted with UF6 and with hydrogen gas, and that reduces the UF6 from UF6 to UF4 and puts it back into the salt. So now we've got a clean salt that has been refueled with uranium and is ready to proceed back into the reactor. The upshot of introducing hydrogen and UF6 together is we're going to make HF. And HF is going to come out here and be introduced into an HF electrolytic cell and be split back into the reactants. Hydrogen and fluorine for the fluorinators, right there. So where do all the fission products go? Well, they come out here as a stream 54, and if we've done this right, there's no actinides in there. because the only actinide we had in the salt was uranium and neptunium, and those came out as fluorinated gases and were introduced into the reduction column. So if we can do this right, we're going to get an exhaust stream that doesn't have actinides and is going to have those favorable decay properties that we want to have over time. Yesterday, I was 50 feet away from the EBR-2, which was a fast spectrum reactor built at INL, and I saw the pyroprocessing facility process the fuel. It was very interesting, but I now actually think this is incredibly simple compared to what I just saw. In the big picture, this system is essentially like the kidney for the reactor. Okay? If you think about the flow of the, I wish I'd come out, that was actually Alvin Weinberg came up with that concept. But you know, your body all the time, your bloodstream is always being processed. It's changing the pH of your blood, it's adding glucose, it's taking out waste products. It's an amazing chemical factory keeping you going. And this is an analogy to what we're trying to do in this reactor. We're trying to put in the good stuff, we're trying to take out the bad stuff so that we can keep the thing rolling. If we can do this, there's a very important implication for this, and that is that we can run the reactor just about continuously. In today's reactors, we have to shut them down about every 18 months, depressurize them, take the lid off, shuffle about 2/3 of the fuel around, take 1/3 of it out, put 1/3 new fuel in. It takes about a month to do that. That's a downtime that those utilities are not making any money when the reactor is being refueled. So to go from a reactor that has to be shut down about every 18 months for refueling to a reactor that can continuously run because we have this chemical kidney attached to it represents an economic advantage for a company or utility or an organization that might use a reactor of this type. Nobody wants downtime. Doesn't matter what, we don't want our car in the shop, you know, we don't want our factory not running, and this technology has the potential to minimize that downtime.
All this is in containment, I'm assuming.
Yeah, this is all in containment. This is not only in containment, this is in structures very similar to what I saw yesterday, hot cells like they had at INL, and not just hot radiologically. These would probably be quite hot temperature-wise as well. I mean, the order of 500-600 degrees. So these are high temperature processes. High rad fields, high temperature. I saw a cell yesterday at Idaho, and they said, it was the HFEF, if any of you have ever been there before, and they said, you know, this facility was manufactured in 1974. And I said, I was also manufactured in 1974. And they said, nobody's been in there since 1974. Okay, I'm a mechanical engineer. I'm not a chemical engineer. I like to talk about power conversion systems, and I didn't design the supercritical carbon dioxide gas turbine system, but boy do I admire those who did work on it, because it really is remarkable. Hare and I got really excited about this. In fact, the very first time I remember we were emailing each other, we were talking about this. It was about the idea of coupling gas turbines to high temperature reactors, and Perry had written a paper about molten salt, liquid metal, different reactors that you could couple through what's called an indirect gas turbine cycle. Now, we use gas turbines all the time today to generate electricity, but we're burning gas in them and they're open cycle. But they have very low capital costs, and that's a great feature, and we really, really do love that about gas turbines. This is what a gas turbine site looks like. You know, nuclear guys like us would love to get to the point where we can build a reactor that's got this simple of a footprint, that's this fast to put in. I don't think we're quite going to get there, but it would sure be a goal to try to get a whole lot closer to something like this, which is a GE gas turbine installation. So could the advantages of gas turbines be coupled with the reliability of nuclear energy? Because gas is expensive and the price fluctuates, and utilities hate the fact that the gas goes up and down because they don't know what they're buying when they put a gas turbine in. Just yesterday I was in Salt Lake City driving from the airport, and day before yesterday I was in Salt Lake City, and there is a gas turbine plant, like right where two major intersections of two major freeways are. And I thought, wow, you know, obviously it doesn't scare anybody at all to put a big power plant right here in this spot. Probably wouldn't get to do that with a nuclear power plant, but that just kind of gives you an idea of the versatility and the simplicity. So utilities love the low capital cost, they don't like the price volatility. So if we can try to combine the stability of nuclear operation with the low capital costs of existing gas turbine plants, we're going to get a lot closer to something that people are going to be interested in. And the thing that's just so cool about the supercritical carbon dioxide system is carbon dioxide is used at very high densities in this, compared to other gas turbine systems. I mean, if you mess around with gas turbines, you're used to a pretty low density fluid. If you mess around with steam turbines, you're used to a very low density fluid in your low pressure steam turbines. And if anybody's ever been to a nuclear plant, anybody been to PWR, BWR? You seen a low pressure steam turbine? Is it small? No, big. It's a big old monster, because the steam that's in there is only a few percent of atmospheric pressure. I mean, it's pretty close to a vacuum in there. Now, feast your eyes on this, which is the densities of this carbon dioxide in this system. Look, the lowest we ever get is about 58 kilograms per cubic meter. Put atmospheric air is about 1. Water's 1,000. Right before it goes into the main compressor, I mean, look at that. You're up at like 716. So that's a fair fraction of water. You're working with a gas that has densities like water. So what do you think that's going to mean for the size of your turbo machinery? Whew. Real small. I mean, you could conceivably lay out the turbo machinery for this thing on this table. The turbines and the compressors. Now the heat exchangers are a lot bigger. But, but I mean, we are talking some really, really small turbo machinery. And it's all driven by the fact that carbon dioxide at these temperatures and pressures is a really dense gas. And that's just amazing. That's just amazing. The other thing that's really cool about it being a really dense gas is it's an awful lot easier to compress. Its specific heat changes as it gets close to the critical point. And so when you go to compress the carbon dioxide in the main compressor here, here's the main compressor, here's the recompressor. In the main compressor, it takes a lot less work to recompress the carbon dioxide because of where it is in its TS diagram. And that's just amazing. Now the recompressor is much more in a more ideal gas region of the TS diagram, but the main compressor is in this just remarkable critical region. And the upshot of that is we're not used to, in gas turbines, to compression being easy. Compression is always the price you pay for a gas turbine. Steam turbines, they spend very, very little of their work on compressing water because they're compressing a liquid, doesn't take much work. But gas turbines have to spend a lot of their work on compressing gas.
What's the maximum temperature you have on the CO2? The turbine.
Yeah, this is this was a 550. This was a 550C. So this is really it can go better than that. I was being intentionally low. So this is a fairly conservative turbine inlet temperature. This is not trying to go push anything. If you were working with helium, you'd really have to go to higher turbine inlet temperatures to get this kind of performance. The other thing about this is a 45% efficient machine, which is just amazing. I mean, that's incredible. I talk to people that are working on the ultra supercritical steam turbine work with Department of Energy. This is about using coal-fired power plants to go to really, really trying to push a few more percent of efficiency out of steam turbines. And I mean, they are working on all kinds of new alloys and this, that, and the other, just trying to a few more percent. Here's a system that's running at pretty humble temperatures and getting 45% efficiency. And again, it goes back to those remarkable properties of carbon dioxide and the cleverness of what's called the recompression cycle, which is what's implemented.
Are any of these commercial?
No, none of these commercial. But the Department of Energy has made CO2 gas turbines a real high priority. They're putting about $50 million next year into CO2 gas turbines. And it's not just, nuclear is just one of different technologies that's looking at it. Concentrated solar is looking at it because it does a lot of neat things for them. Fossil's looking at it a lot. And there's a lot of different variants of it too. Like when you look at a fossil one, they sometimes use exhaust gases as the carbon dioxide and then use these high pressures to help them go and sequester carbon dioxide. So there's a lot of really kind of clever, interesting things you can do with this cycle. But I love it because it really seems to be a very natural fit with the temperatures and the performances on this reactor. And it also helps address another important issue, which is we're going to be generating tritium in this reactor from residual lithium-6. And the tritium has to be captured. And I'm kind of assuming in this design all the tritium makes it to the carbon dioxide. And that's one of the reasons I chose carbon dioxide is because it doesn't have any hydrogen in it. So if there's any hydrogen in your CO2, it's tritium. And you need to get it out. So there's ways to do that, and particularly by taking advantage of some of the lower temperatures. This is not exactly the kind of reactor core that we're going to use, but it's fairly representative. It's mostly got graphite structures inside, and then the fluoride salt flows up through channels in the graphite, and inside the reactor, that combination of the graphite and the salt together are what enables the fission reaction to take place. And it has to do because the graphite serves the important job of slowing down the neutrons. So salt and graphite together, you can have a nuclear reaction. If you take them apart from one another, the reaction is going to stop. It's just laws of physics. There's nothing you can do to change it. And that leads to a super important safety feature, one that I find very compelling. We saw what happened when the reactors in Fukushima were deprived of emergency power. After a while, there were some unpleasant results that took place there because they were not getting their coolant pumped around. They were not able to keep their fuel rods cool, and some radiation was released. On the other hand, in this design, the fuel is already melted. It's melted at a much lower temperature than conventional nuclear fuel melts at. That stuff is ceramic. This is salt. This allows us to use a feature called a freeze plug in order to keep this whole operation running. This is the nuclear reactor vessel. The idea is if you were to lose all power, then the little blower that's been blowing, keeping that salt frozen in that line, stops blowing. And the energy from the reaction melts the salt, and the salt drains out into what's called the drain tank. And the drain tank doesn't have the graphite in it. So there's graphite up here, there's no graphite down here. Without graphite, the nuclear reaction can't happen. It can't take place. So you've taken away the two ingredients. When I was a Boy Scout, we always learned, you got to have oxygen and fuel and a flame, and that's how you make it go. In nuclear reactors, you have to have moderator and fuel, take them apart, and it's not going to work anymore. So this very simple feature moves the reactor's fuel into a configuration where continued fission is impossible. It's a fail-safe shutdown system. It doesn't require the operator to be involved, doesn't require anybody to throw a switch. Even if the reactor is severely damaged, there's a catch pan here. If you were to breach that vessel, the salt would flow down the catch pan and still back into the tank. So it is a very, very safe configuration, something that can be used to eliminate a whole class of accidents that we are concerned about today, and something that personally, would make me a whole lot more comfortable with the widespread use of this technology. So this is something that was demonstrated at Oak Ridge back during their operation in the 1960s. They were able to turn off the reactor, melt the salt, and drain it away safely. There's another picture of what this drain tank might look like and how it is designed to reject the generation of energy taking place within the salt just due to its decay. We're still going to face a lot of challenges in developing this technology because, quite frankly, it's been set down for about 40 years now, and we really need to pick it up again. One of the biggest challenges is we need to get qualification of the materials we're going to use, particularly a high nickel alloy called Hastelloy-N. This is what they built these reactors out of. It was a special alloy that was designed expressly for use with fluoride salts. It works very well. Unfortunately, we don't make very much of it anymore, and we need to get the code qualification case. Good news is we're talking to the Department of Metallurgical Engineering, so this is a no never mind for you guys, right? Okay, good. Now I'm feeling a lot better. Several other things we need to be able to do. We need to be able to remove noble gases from the system. These are some of the fission products. We need to improve our pump designs, heat exchangers, and particularly we need to begin investigating these chemical processing systems. Yesterday I was given a tour of a radiochemistry lab here at the U where some of these processes are beginning to be investigated, and it was really exciting. And I'm hopeful that with further funding and additional people working on it, we're going to be able to investigate even more of these processes and hopefully really move this technology forward. And I think that you can be a great part of that. I'm going to conclude with a quote from Alvin Weinberg, and he was a gentleman at Oak Ridge Lab who led the lab as they were developing the molten salt reactor and the thorium fuel cycle. He said, "During my life, I've witnessed extraordinary feats of human ingenuity. I believe this struggling ingenuity will be equal to the task of creating the second nuclear era." I spoke to Dr. Weinberg in 2006, right before he passed away, and he said, "My only regret will be I will not be there to witness the success." If we are able to bring about a thorium-powered world, a clean and sustainable world based on this remarkable energy source, we're going to owe a great debt of gratitude to this man and the hard work that he did. And I really hope through working together we can bring this future a whole lot sooner than we might have thought. Thank you very much for having me here. I'm happy to take any questions.
Dr. Dewan testified before one of the House subcommittees about a month ago about the fact that there is no regulatory mechanism to license new reactor designs.
She and I have both participated in DOE activity for the NRC where they are looking at this problem. They're going and they're saying, hey, we realize there's going to be a need for advanced reactors. It's a licensing initiative that's been taking place. And they took commentary. My company submitted recommendations and suggestions. I think a number of people did. We had supporters from the thorium community that attended these public meetings in DC. And our licensing guidelines today were designed around the kind of reactors we have today, light water reactors. And we need to kind of pull back and look at nuclear in a more general sense, saying, okay, that's a kind of nuclear reactor, but there's a bunch of other kinds, and we need to be able to have the guidelines for it. For instance, if you were designing a molten salt reactor, you'd want to have a guideline that said you're going to have a freeze plug, you're going to have a drain tank, you're going to have those things in your reactor so that if you lose power, it's going to do certain things, and that would be part of a new regulatory framework. Of course, that rule would not be applicable to solid-fueled reactors, but it would definitely be applicable to a molten salt reactor. And so we're trying to do the best we can to let the Department of Energy know that there is interest in not just in advanced reactors in general, but specifically in molten salt reactors.
Thank you for your talk. My question is that it's related to that last concept about draining the core. As I see it, you'd have to separate the liquid fuel into multiple separated parts, so that when you drain the thing, you don't go critical when you drain all the fluid into one place.
You can't achieve criticality because there's no moderator. That was the point I was trying to make, was once you separate from the graphite, criticality is impossible. There's simply not enough fissile content in order to achieve criticality.
Okay, but what about needing to cool that like with water or something to cool decay heat and things in the...
Well, yeah, I mean, you need to have kind of fingers in there that are taking thermal energy out. Oak Ridge looked at using NAC, they looked at using sodium, they looked at using lithium beryllium salt, looked at using water. There are a lot of pros and cons to either one. There was not a clear, obvious, oh, this is the right one. Right now, surprise, I'm favoring using salt, but you know, there's other possibilities. But yeah, the big important thing about the drain tank is drain tank doesn't have any moderator in it. Without moderator, recriticality is impossible. And that's not the case with fast spectrum molten salt concepts, because they don't rely on a moderator. So in their case, when they drain, they need to go like that. They need to go to different separate drain tanks so that recriticality becomes possible.
I can add to that the drain tank is very hot, up to like 700 degrees C or maybe 900 degrees C. And so radiant heat removal is very feasible. So in the Thorcon design, there's just a large surface area tank with a panel wall filled with water nearby. And you don't need any pumping.
One of the issues with the conventional nuclear power is that it has a very slow response time. So with the emergence of renewable energies such as wind and solar, you need to build supporting power plants for when those wind turbines aren't producing. Like, for example, when you put a wind farm in, you need to build a gas-fired power plant to supply the energy for when the wind is not available. So conventional nuclear isn't a good backup power because it can't respond to the changes in the grid fast enough. Would this thorium reactor have a faster response time than conventional nuclear, and would that then be a candidate to fill in that gap when you have put in renewable energies?
Yes, it is more responsive. It is substantially more responsive. And the reason why is the thing that causes conventional nuclear to lag in its response is the buildup of a particular fission product called xenon. It causes solid-fueled reactors to be limited in their response times to changes to transients. In a liquid fuel, the xenon comes out of the fuel just like fizz comes out of soda pop. And so it does not limit the response time. That said, though, I will confess to having a little bit of a dim view on the use of wind power. I believe if you've got a reliable source of energy, use the reliable source of energy. Don't turn it off when something unreliable decides to show up.
What kind of temperatures would the reactor typically be operating at, and how does that impact the material performance?
The salts themselves are not limited very much in their temperature range. They'll go up to about 1400 C before they start running any troubles. The Hastelloy material we want to use in the reactor, though, chromium ion migration in Hastelloy metals is what takes place, and that accelerates the corrosion of metals. So by staying below 700 C, we really limit that corrosion rate. The beautiful thing about the carbon dioxide gas turbine is that it really has a sweet spot right there at about 500 to 650 C. That's really where it wants to operate and has the best efficiencies. And that gives it a big advantage over other potential gas turbines which want to go higher and higher in temperature.
How much interest is there in this design by major nuclear power companies?
I've spoken to several utilities, and there is growing interest in some of these utilities. There's also been interest at the Electric Power Research Institute, which is the R&D arm for U.S. utilities. I've had several meetings with them, EPRI, and they continue to express interest and want to learn more about the technology. So it's growing. You know, it's not a... I don't want to say we don't have any orders right now or anything like that, but I think we're talking to the right people, particularly EPRI, about this technology.
Are there competing designs like some of the newer breeder reactors that are serious competitors for this?
Well, there's other concepts for molten salt reactors that are being put forward. They're not breeders, and they don't use thorium, but they're being advanced for other reasons. There's a group out of Canada that wants to do a uranium-fueled molten salt reactor. There's another group that wants to consume nuclear waste out of a molten salt reactor. Both are, admirable goals. What I think is amazing about molten salt technology is the fact that the thorium fuel cycle integrates so cleanly with the technology. And the thorium is going to be the key to the long-term sustainability of nuclear energy. You can use thorium in existing reactors, but the economics aren't there to support it. It's very, very difficult to use it as a solid oxide fuel in existing reactors and to go through the processing. The advantage for the molten salt is that processing is much simpler, and it reduces the fuel cycle costs and makes a breeder a conceivable economic proposition for a potential utility. Outside the U.S., there is a large effort going on in China on all reactor types, but the one I focus on is they are working on thorium molten salt reactors. They are putting hundreds of millions of dollars a year into this technology, and that is vastly in excess of anything that's going on in the West. So, as you saw, this technology was invented in the West. It can benefit everyone. I welcome the fact the Chinese are working on it. I think we should be working on it as well.
So what do you anticipate the economical size of your first reactor is going to be in megawatts, and then what kind of physical size would it require to put on site?
Well, the first reactor we would build would be a research and demonstration reactor, not terribly dissimilar to the molten salt reactor experiment you saw. It would not be intended to generate electrical energy. It would be intended to advance the technologies, probably on the order of just a few megawatts. Wouldn't make any electricity. It would just be about doing demonstrations of the different physical things you'd built it out of, the Hastelloy, the graphite, etc. Wouldn't be optimized to be very compact either, because when you're doing development, you kind of want to spread things out so that you can check things.
I was asking about what do you envision?
Oh, for a first commercial reactor? Yeah, we're shooting for that 250 megawatt size reactor, and this is probably a pretty good sense of about how big that would be. A physical footprint of probably 2 football fields or so with coolant systems and so forth.
And you talk modular, so I'm assuming that means instead of scaling up the reactor to more megawatts, that you would add more modules.
Exactly, yeah. That's the idea of saying rather than building one really big one, if you want so much power, we're going to add, that number divided by the modular power, and that's how many we'll put in there. And that's becoming more interesting to people because they don't want to have to go out in the field and build reactors. They want to build them in a factory, ship them to a site, and essentially almost plug them in.
What's the minimum size?
I always get the minimum size. Well, here's why the minimum size doesn't matter, because the NRC assesses a $5 million a year licensing fee. So it doesn't matter how small you can build it. If you don't build it bigger than about 50 megawatts, you're not going to make your money back.
Now, your picture implies you need a large body of water for cooling.
This picture was actually meant to imply that we're going to desalinate seawater with with the waste energy of the plant. So if we were parked right next to the ocean, yes, we'd very much want to desalinate seawater and provide fresh water in addition to electricity.
Now, if you're not next to a big body of water, is there a lot of waste heat?
With the highly efficient carbon dioxide system, we're going to reject less waste heat than any other power plant that was going to operate at lower powers. Like, let's say you had a coal plant at 40% or a conventional nuclear plant at 35%. If you're running at 45%, you're going to reject less waste heat than that. And the other thing, too, with this carbon dioxide gas turbine, there's the potential to reject waste heat directly to the air as well, not even having to use bodies of water. Now, there's an economic penalty for doing that. If you're next to a body of water, you'll probably want to use it. But there is the option, though, to potentially go and put these in places where the water isn't present. And that's not an option for today's reactors. They have to be located near large bodies of water. It's something I thought about a lot with Utah. So we have a lot of water out in the eastern U.S., a lot of places to cool reactors. Here in Utah, we don't have so much. And so this type of technology would make a lot more sense for Arizona, Utah, Idaho, Nevada, places that don't have nuclear power now. And a lot of that has to do with the lack of cooling water.
Well, plus a lot of excess of heat into bodies of water can have quite an ecological impact.
But that can really be mitigated, and that's common to pretty much every form of energy. I mean, even concentrating solar has to cool their steam.
Way less than that, though.
For the power rating it has less. Per unit megawatt, it's gonna be less waste heat to the environment.
How open are you to foreign investment to get the wheels spinning?
Well, it's super open if you know of any.
Or For example, the Emirates, they're looking at.
Oh, I've been there, talked to them, and they say, well, I'm not saying I spoke to the sheikh or anything like that, but essentially what I heard from the people there was, Kirk, sounds great. As soon as you built one in the U.S., let us know. We'll take a good hard look at it. You know. So what I found is I've gone to Europe, Singapore, Dubai, Australia. Everybody still wants the U.S. to go first.
Prove it.
Yeah, they love the idea that you guys go, see if it works, and if it works, we'll be happy to take a good hard look at it.
So they don't want to research, they just want to.
The exception to that is China. China's going and doing it. They're not waiting for anybody, they're going to go make it happen.
In addition to the electrical generation, there's hydrogen generation for fuel cell.
There is the potential for that. There's a very interesting hydrogen generation technology that's been developed at Oak Ridge that looks also like it would couple very well to the reactor, and hopefully we're going to be able to investigate that.
Yes, follow-up to that is medical isotope production.
Yeah, there's a number of potentially interesting medical isotopes that you could generate from this reactor. I mean, one of them comes from the thorium fuel cycle itself. Uranium-233, when it decays, will decay to an isotope called bismuth-213. And I attended a seminar 2 years ago where they talked about using bismuth-213 to fight some of the nastiest cancers you can think of. Leukemias, lymphomas, glioblastoma, which is a terrible brain cancer. And the results were amazing. And what they said was, we are real limited on how far we can go with this because we don't have very much uranium-233. Uranium-233 only comes from thorium. So if we were operating these reactors, they would essentially be producing a material just in the course of normal operation that could change the fight on cancer completely. And it's proven. I mean, there is medical data to show that it's called targeted alpha therapy. If you want to look it up, targeted alpha therapy using bismuth-213 is an incredible technique against some of the nastiest forms of cancer, and it's uniquely coupled to the thorium fuel cycle.
Add a revenue stream for the utilities.
And potentially as well. I mean, it's just amazing stuff. I think in the future when targeted alpha therapy becomes a more widely used form of cancer therapy, we're going to look back on what we did today as like sticks and stones.
I think I did a talk at Oak Ridge a couple of years ago, and they were talking about a modular reactor project at Clinch River. And if I understood it correctly, it was to be put underground with no large external containment vessel, both for safety and for reducing cost. Is that a possibility with this?
The program you're referring to was run by Babcock and Wilcox. It was called their M-Power reactor, and it was going to be underground. It did have a full containment built around it, though, and it was going to be built at Clinch River. Earlier this year, Babcock decided to dial down their involvement with the M-Power project, and just a few weeks ago, TVA announced that that site, instead of being specific to that particular small modular reactor, is now going to be hopefully a small modular reactor development site where they will try whatever reactors are ready. And that got me really excited because I thought, well, hey, you know, maybe I'm perhaps dealt back in the game because I would really like to see liquid fluoride thorium reactors developed and operating near Oak Ridge. And the Clinch River site is not very far at all away from Oak Ridge. Guys, it drives me crazy. The Oak Ridge National Labs, one of our pioneers in nuclear energy, has never been powered by nuclear energy. It's powered by coal. You know, that's just crazy.
What do you anticipate the timeline for this project to be? Will we see it in our lifetime?
Yes, you will see it in your lifetime because that's what I'm going to go make sure happens. I'm going to need some help though. So, but yeah, I don't mean for this to be a multi-generational development. Although I have instructed my kids they're supposed to continue on the work no matter what happens to me. I got to tell you, studying Glenn Seaborg's life in considerable detail, I just can't believe how awesome and how fast things can go when you get the right smart people together and you got the funds. And I mean, the Manhattan Project, although it was done by hundreds of thousands of people, if you look at how many people were working at Chicago on reactor design, chemical processing, we're talking less than 100 people, right? Less than 100 people figured out this whole big thing that became Hanford and all these other parts of it. So it's not a problem that you need to huck thousands of bodies at. It is a problem that can be done probably better by a team of 50 to 100 engineers.
You know, I think in the United States there is a large, well-funded, though somewhat clandestine, anti-nuclear group that's going around targeting nuclear reactors to close them down for whatever pathetic, legal, bureaucratic reasons they could find. San Onofre for one, and Vermont Yankee for another.
Yeah.
How do you intend to deal with that?
A few weeks ago, Vermont Yankee shut down, which had been running for 40 years and sustaining the economy of southern Vermont. And a lot of people who were against nuclear came from out of town, pressured the governor and the state to shut it down. They did so, and those people are all gone now. But the people who are going to suffer from that shutdown are still there. And I think having a clean energy source that's not polluting the air is a great thing. I live 20 miles downwind from the Browns Ferry nuclear reactors. They sit on the Tennessee River and they provide clean energy for Huntsville, Alabama, and I'm really, really grateful for that. They're not perfect, you know, they're first generation reactors. Ultimately, I'd like to see us be putting thorium reactors out there and chewing through the nuclear waste that was generated during the operation of Browns Ferry. But I think it's, you know, eventually reactors reach the point where you do need to shut them down. You know, they don't run forever. But I don't like what's happening with reactors that have a lot of life left in them being targeted for shutdown by anti-nuclear groups who then sort of come to town, protest, and leave the community cleaning up the mess. San Onofre, I'm glad you brought that up. You know, the people of San Diego are looking at a multi-billion-dollar cost because San Onofre was shut down years earlier. That reactor could have been generating clean electricity for Southern California, and now it's sitting there as a big political liability. Way to go, you know. So, I think you had one.
As far as like the activists, it seems like a little education. You could bring the activists into your camp.
I certainly hope so, and I've noticed on an individual level that does seem to happen. On the command and control level, though, don't seem to make any progress. I bring it up because one time I was with Baroness Worthington, who's a member of the House of Lords in London. She used to work for, you know, Friends of the Earth, and she took me over to their office in London, and we gave them a full briefing, and they said that, well, we're going to be really open-minded about this. We're going to take a look at it. And then not long afterwards, I heard them, same guy who sat there in my lecture, get up and say, we're fundamentally opposed to all forms of nuclear power. And I wanted to say, you know, we have the same goals here. We want a cleaner world. We want a safer world. Here's a technology that mitigates the issues that you claim to have with nuclear energy. Can't you take a look? You told me to my face you could take a look at it. Why can't you take a look at it? Why are you issuing these closeout statements to people that I don't even want to think about anything about it? What I find a little strange about the conventional environmental groups is they seem to have unbounded faith that wind and solar are going to improve and improve and improve. But they seem to exercise no faith whatsoever that nuclear energy, a technology which right now is 0.5% fuel efficient, can ever get any better. And I see amazing amounts of potential efficiency improvement possible in nuclear. In a former life, I was working for NASA. I actually spent a lot of time working on solar energy, and I don't hold out as much hope that solar energy is going to get a lot more efficient. It can. It's just the problem is it gets a lot more expensive. I used to have a solar cell the size of my business card that was for satellites. It was 30% efficient. It's top of the line. Cost more than my car. You know, there's the reason we don't use that technology. We use stuff much less expensive and much less efficient in solar panels. So I have a lot more faith that we're going to be able to improve nuclear and take advantage of that 2 million to 1 improvement in energy density. I wish that faith was shared by some of the more well-known environmental groups. So,
something like that could get small enough to operate large vessels like...
Oh, absolutely, absolutely. You would be amazed how much of our pollution is caused by large ships. The ships that are transporting our goods back and forth across the ocean, they burn a fuel called bunker fuel that's, I'm told, it's kind of like asphalt. It's just about the nastiest stuff you can burn, and so they make lots and lots of pollution. And because they do it on the high seas, it's not considered under anybody's jurisdiction. If you could replace some of those large transport vessels with a clean form of energy, you'd get rid of a lot of pollution.
Is it politically or technology-wise that's slowing down the progress of the lifter reactor?
We need funding, quite frankly. I mean, everything runs on funding, and so you've got to have the resources to get the engineers, the scientists, the experiments done, the labs stocked. One of the great things I saw yesterday here at the U is due to some investments by the state, you're building laboratories here that are starting to be able to do experiments that are totally relevant to this technology. I mean, that's really exciting. That's showing how an investment that's being made at the state level is going to reap benefits. I really hope Utah gets out in front of this. Nothing would please me more as a fifth-generation Utah to come and see this happen in Utah. So, again, thank you so much for letting me come. I really appreciate your attendance today.
And it's going to be fun to have you visit around the rest of the day. We'll have some tours also, and you'll be able to see some of the stuff that we're doing.
Excellent. That's what I'm here to see.
Thank you, everyone. It was a really great, inspiring talk.